Here we are in Berlin 1969. Mr. Gott, a young man, arrives in West Berlin and attempts to cross to East Berlin. However, he finds that there is a wall which prevents him from crossing to East Berlin. He also learns that this wall has been there for 8 years, i.e. since 1961. Just based on this information, young Mr. Gott thinks to himself, that means the lifespan of this wall is between 8.2 and 320 years, and I am 95% sure that is the case. That is an interesting hypothesis, and we will try and understand how Mr. Gott came to this conclusion and how justified he is in that conclusion. Before doing so, it's important to define another random variable, and this random variable I will call t. T will represent the current age of the wall when Mr. Gott arrives in Berlin. In this particular example, t is equal to 8, but treating it as a random variable means it actually has a distribution. And Mr. Gott claims, because he had no prior knowledge, he is equally likely to arrive at any point in the lifespan of this wall. So t has a uniform distribution between 0 and L. It's important to realize that t is a continuous variable, so what we have here is actually a probability density function. Okay, so now to try and understand where these 95% confidence interval came from, let's use the frequentist approach. So, first we can confidently say that t being in the interval 0.025L to 0.975L, shown top right, has probability of being 95%. That simply comes from saying we technically want to integrate the probability density function between 0.025L and 0.975L, but we can quite clearly see that's 95%, given the height of the uniform distribution will be 1 divided by L, as a probability density function integrates to give 1. Now that we're happy with this first statement, we can try to do some kind of manipulation. First, we will separate the inequalities into two separate inequalities, so we can write the probability statement as a joint distribution. So we have written this as two separate statements, two separate events, and we haven't actually changed anything in the statement itself. But now we will do some simple rearrangement of each inequality. For the first inequality, we divide it through by 0.025, and for the second event, the second inequality, we have divided through by 0.975. And this whole probability is still equal to 95% because we haven't actually changed the probability itself. If we sub in the fact that Mr. Gott arrived at t is equal to 8 years, we get, voila, his prediction that the lifespan must be less than 320 years, but more than 8.2 years, with a 95% confidence. So it seems Mr. Gott is justified. However, this is not the only approach to this kind of problem. We can try and identify the distribution of L, the lifespan, using a Bayesian argument. Before doing so, we have to define some things. First, we have to treat L as a random variable. So far, we've just been treating it as some unknown variable, which we've been carrying through our algebra. But what we want to do is treat it as a random variable which has its own probability distribution. More specifically, we want to capture the information that t is equal to 8 years by modeling the posterior over L. That means we want to know the distribution of L given t. Specifically, t is equal to 8. In general, in machine learning, when we have a posterior, we may attempt to estimate the actual value of L, or get a good estimate of the value of L, using something called the maximum a posterior, which is basically selecting the value of L that maximizes the posterior distribution, which seems like a sensible and perhaps intuitive thing to do. But we're not going to quite do a map estimate here. We're going to try and identify the entire posterior distribution, so we can identify the 95% interval of this lifespan. Okay, so we can use Bayes' rule to actually evaluate the posterior. We can say the probability of L given t is equal to 8 is equal to the probability t is equal to 8 given L times the probability of L divided through by the probability of t is equal to 8. That's a lot of maths and quite a mouthful to say, so we'll try and break it down into more intuitive terms. First being the likelihood. The likelihood of L, specifically, is where our variable L is already given. We actually are lucky here. We know the likelihood. If you look in the top right corner, it is a uniform distribution, where we know the probability of t is equal to 8 given L is equal to 1 over L, like any other value t would hold in this lifespan. Next, we have the denominator, and we call this the evidence in machine learning. This can actually be written as an integral. If you remember, t is a continuous variable. So if we demarginalize it, so recall the definition of marginal, if we demarginalize t, we don't use summation signs, we have to use an integral sign, which you all know is simply a summation sign with an infinitesimally small iterator. And if you look at the terms in this demarginalized form of probability t is equal to 8, we have the likelihood again, probability t is equal to 8 given L. But now we are varying through the different values of L. Finally, we look at the final term in this fraction, and that is the prior, the probability of L. It is interesting to note in this problem, we don't actually have a prior in this problem, which makes one think, okay, so if one was to choose a sensible prior in L, it could be a uniform distribution between two intervals, it could be a normal distribution, it could be almost anything, to be honest, which is sensible from our experience of wars in history or any other experience an observer might have. So if I think to myself that I choose some prior, how is it likely that it will give the same result as a frequentist argument? The answer is, it's not likely. There has to be only one very specific prior which will give the same result as the frequentist argument. So in general, Mr. Gott could be wrong from a Bayesian argument or a Bayesian approach if we choose a prior which does not cause the same result as the frequentist argument. So the point of this exercise is to show that a frequentist approach and a Bayesian approach can give very different solutions to the same problem. And to make them compatible, you have to choose a very select prior to make the Bayesian fall into the category of the frequentist argument. And that is that for this time.